This worksheet is about identifying what the nucleophile is that will be reacting with the reactant and in what orientation will it attach. So for the first compound here, we have 1, 2, 3, 4, 5, 6. This is a 2-iodohexane, and we have some specific stereochemistry here with the heteroatom being 1, this part of the molecule being 2, and this part being 3. We are rotating in a counterclockwise fashion, but H, the implied H, is coming out towards me, so this is an R2-iodohexane. So the nucleophile here is going to be the bromine. Remember, our nucleophile is going to be either something negatively charged or something with a lone pair of electrons, maybe a pi bond. So here we have a bromine, and this bromine is going to react in an Sn2 reaction. It's going to come to the electrophile, which is the carbon that contains the heteroatom, which will remove the heteroatom. So when we are done, we should have 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. Let's draw it the same orientation. Yeah, like that. We will have bromine being attached on a wedge. And the reason it's on a wedge is because the original heteroatom was on a dash. So that's how we can tell the stereochemistry. Now we can name this. This is going to be a 2-bromohexane. And this really should be an S, but let's double check. So the heteroatom gets 1. This part of the molecule gets 2. The methyl group gets 3. We are rotating counterclockwise with the H behind us, the implied H behind us, which makes this an S. So that is correct. For B, here we have 1, 2, 3, 4, 5, 6, 7, 8, 9. A 9-carbon chain. That makes this a nonane. And specifically, this is 2-bromononane. We do have some stereochemistry we need to take into consideration. This is a wedge. It looks like a stick, but it's a wedge. And we need to assign our CIP priorities, with bromine being 1, this side of the molecule being 2, and this side of the molecule being 3. The H is implied and behind us. So we are rotating counterclockwise, which makes this an S2-bromononane. The nucleophile we will be reacting is iodine. Remember, when you see a metal in this class, 99% of the time it will be delivering an anion. So here we have potassium iodide. Potassium is a metal. It is delivering the iodide anion. So that is going to react in an Sn2 fashion, coming right to the electrophile. So that nucleophile, our arrow goes from the nucleophile to the electrophile, which then pushes the heteroatom off. So then the product that we have, oh goodness, I need to draw 9. 1, 2, 3. Not quite. 2, 4, 6, 8, 9. 1, 2, 3. I said it was 2. It's 4. It's 4 bromo. I don't know what I was thinking. 1, 2, 3, 4. So because the bromine is on a wedge, I'm going to put the iodine on a dash. So that way I have inverted the stereochemistry. This should be R4-iodo-nonane. That's what it should be. So let's double check. 1, 2, 3, 4. So we have iodine gets CIP 1. This part of the molecule gets 2. This part gets 3. We are rotating counterclockwise, but the implied hydrogen is coming out towards me, so that is an R. For C, I'm going to erase this stuff at the top just because we don't have a whole lot of room. We have the iodine here is our alkyl halide. That's where we are reacting. You see this methyl group, we're leaving that there. There are 2 stereocenters here, but there's only 1 that will be reacting. So first, let's name this molecule. I'm going to number it from this side because 2, here's 3. I can count 4, 5, 6, and 7. Because we do have 2 substituents, so we need to reduce those numbers. So I have a 4-iodo 3-methyl heptane. And we do have some stereochemistry we need to think about here. The methyl or I should say the asymmetric center with the methyl. This side of the molecule is going to get a 1. The ethyl group is going to get a 2. The methyl group gets a 3. The implied hydrogen is 4, and it's coming out towards me. So I'm rotating clockwise, but that implied hydrogen coming out towards me means that is an S. That is carbon 3. So this is a 3S. And then at carbon 4, the asymmetric center that has the iodine gets CIP priority number 1. The side of the molecule that contains the methyl or the methyl asymmetric center is CIP priority number 2. And then this side of the molecule is going to be CIP priority number 3. The implied hydrogen is coming out towards me. I am rotating clockwise, but with that hydrogen coming out towards me, that means this is a 3S, 4S, 4-iodo, 3-methyl heptane. That's its whole name. So now we look for the nucleophile. The nucleophile is here. It's this methoxy group because remember 99% of the time when you see a metal in here, it's delivering an anion. Because it's delivering an anion, that is my nucleophile. It's the methoxy group. So this is going to be a little awkward, but we're going to come in and usually I would draw the nucleophile coming up under. I just can't do it that way. I need to do it this way. So I have my methoxy group coming towards that electrophile, which pushes the heteroatom off. And then I am left with the product. This methyl group stays where it is. And this time I have a methoxy group that comes off the parent chain. So now 1, 2, 3, it's still a 3-methyl heptane, but now at carbon 4, I have a methoxy group. So this is a 4-methoxy 3-methyl heptane. And the 3S didn't change, but we should have a 4R now. So the oxygen is our heteroatom. That's 1. Here's 2, here's 3. We are still rotating in a clockwise fashion, but this time with the H receding behind the page or the piece of, or the paper or the screen, then we have an R. So that asymmetric center does shift. That's 3S, 4R, 4-methoxy, 3-methyl heptane, which is C. For D, here we have this, our nucleophile it's structured a little bit differently, but we still have this metal. See the metal? The lithium is a metal. It's on the left side of the periodic table. Therefore, it is delivering an anion. So this is a methanide. That's what it's called. But usually you're not asked to name the nucleophile as much as you're just asked to identify it. So this is my anion, and it will come towards the electrophile here, pushing the heteroatom off. So when I draw the product, don't lose any carbons. When I draw the product, then that methyl group is going to be on a dash, but we didn't name it. I should have named that too. So what we have is the longest carbon chain that contains our functional group. So we would call this a pentane, and I'm going to number it the other way. I'm going to number it this way so that I reduce the number of my substituents. So this is a 1 cyclohexyl 3-iodo pentane. That is my reactant, but I do have some stereochemistry I need to take into account. So the heteroatom gets a 1. This side of the molecule gets a 2. This side gets a 3. The hydrogen is implied and pushed behind us. We are counterclockwise. That means this is an S, 1 cyclohexyl 3-iodo pentane. So the product then, we're going to number that the same way. And this is still going to be a 1 cyclohexyl. Oh, I just realized I'm running off the screen. So 1 cyclohexyl 3, this time 3-methyl pentane. We do have to talk about that stereochemistry. It should be an R. Let's double check. So we have our group 1 is this side, group 2 is this side, the methyl is 3. We are rotating counterclockwise with H coming out towards us. That is an R configuration. For E, our nucleophile is going to be the iodine. Remember, Metals deliver anions in organic chemistry 99% of the time. So we are delivering this charged this iodide, and it's going to come after our electrophile, which pushes the heteroatom off. Well, let's name this reactant first. Let's see, we'll call it 1, 2, 3, 4. So this would be a 2-bromo, 1-phenyl butane. We do have an asymmetric center at carbon 2. The bromine gets a 1. This side of the molecule gets 2. This side of the molecule gets 3. We are rotating clockwise, but H is coming out towards us, so this is an S, 2-bromo, 1-phenyl butane. When we form our product, I'm just going to draw on top of here because I think I have established that I have a very hard time drawing with this system. So we're still going to number it the same way. This time it's not a 2-bromo, it's a 2-iodo. So that part changes in the name and this part as well. So this should be an R, 2-iodo, 1-phenyl butane. Now let's double check that asymmetric center. So the iodine gets a 1, the phenyl side gets a 2, and this side gets a 3. We are rotating clockwise with the H receding behind us. Therefore, this is R, 2-iodo, 1-phenyl butane. For F, we have a couple of things going on here. We have a D. What does that D mean? Well, the D is called deuterium. Deuterium is a heavy hydrogen species, and we deuterate things in order to see them like on NMR, which is an analytical technique that we'll talk about in the first module of Organic 2 if you're going to be sticking with this series. But the purpose is we need to draw the Sn2 product. So we identify the nucleophile first, which is going to be a charged bromine, because we have a sodium here, and we're going to come in and pop this off. Now, when we do that, though, we do have to invert our stereochemistry. So this might be a little bit awkward. Let's give this a go. So the iodine gets a 1, this side of the molecule gets a 2. The deuterium will get a 3 because hydrogen is going to be number 4. We rotate clockwise, but hydrogen is coming out towards me. So this is an S. So when I make the product, I need to make the product as an R configuration. Now, I wouldn't ask you to name something with a deuterium in it. So I hesitate to even give you that part. If this was a hydrogen, this wouldn't be an asymmetric center, so you wouldn't have to worry about it. But because it is, we need to create our product with an R configuration. So what happens is when the bromine comes here, we rotate around a bit. So we'll flip. So the easiest way to do this, let's do it this way, would be to put the D here, the H here, and the bromine here. And then you have an R rotation. So bromine gets 1, this side of the molecule gets 2, the deuterium gets 3. We are rotating clockwise with H to the rear. That gives us an R configuration. The point is to show the change in stereochemistry. So for G we have this bicyclic compound. I wouldn't ask you to name those in Organic 1. The point is to find the nucleophile and draw the product. So we're going to have our nucleophile come after the electrophile, which is the carbon that contains the heteroatom. The heteroatom will leave so that the product that we obtain changes our configuration. So we were on a dash, now we're going to be on our wedge, and we attach our nucleophile on that wedge. For H, our nucleophile is going to be this methoxy compound because the sodium is delivering an anion. The electrophile is the carbon that contains the heteroatom. As the nucleophile attacks the electrophile, the heteroatom is released. So what we have for our product is we put it on a dash, and then we put the methoxy group on. For I, we have bromine acting as our nucleophile, which comes after our electrophile. We push the heteroatom off, And so the resulting product, because our reactant was on a wedge, our resulting product is on a dash. For J, we need to identify this nucleophile. Now here we have the lithium again on the right, which is a little aberration from what we learned in general chemistry. We usually put the metal on the left. But here we have this methyl anion, and it's going to attack the electrophile. Where is the electrophile? Well, the electrophile is going to be the carbon that has the heteroatom. This is a methyl group. Therefore, it's not a heteroatom. It's a carbon bonded to another carbon bonded to hydrogen. It's not a heteroatom. So we have this nucleophile that's going to come towards the electrophile, which will remove the heteroatom. And then our product will have a methyl group out here on a wedge. This does not change. Nothing is happening there. For K, we have to identify that cyanide, and it's a charged cyanide, is acting as our nucleophile. And it's going to come for our electrophile, which is the carbon that contains the heteroatom. That will push the heteroatom off, and then we will form our nitrile on a dash product. Now for L, we have two equivalents shown, and the reason we have two equivalents shown is we have two electrophiles. So one will go here, one will go here. We will push these heteroatoms off, and when we do that, the product we will form, because our nucleophile is a methyl anion, we will put methyl groups on wedges where we had iodines. For M, this is a conformation of a cyclohexane ring. Our nucleophile is a charged iodine. We will have the iodine come from underneath the ring because the bromine is on top of the ring, and then we will push the bromine off. Now when we do that, and I'm not sure how to show this best, but if I scratch this baby out and then I put the iodine under the ring here. For N, similar to M, our cyanide will come from under the ring to push the bromine off. And when it does that, the product that we form, I'm just going to kind of scratch out the bromine. He is in an axial position, so our cyano group will be equatorial. For O, our nucleophile is the methoxy group. So he's going to come towards the electrophilic carbon. The electrophilic carbon is the one that contains the heteroatom, and then that will push the electrons onto the heteroatom so it can leave as an anion. So the product of this reaction will have our methoxy group, but because the I is equatorial, the methoxy group will be axial. It will be in the flagpole conformation, and we kind of get rid of him. And I realize that looks like a dash. I'm not sure how to get rid of him any other way. And P, we have this thiomethoxy thing. And so the electrons are on the sulfur because remember, we have this sodium is a metal. It is delivering an anion. So the sulfur is going to come up under the ring because bromine is on top of the ring in this conformation, which will push the bromine off. Now the sulfur will attack at the electrophile. The electrophile is the carbon with the heteroatom. So because bromine is equatorial here, then our thiomethyl group will be axial in the flagpole position, and we kind of scratch him out because he has gone away for our product.